In this video, we're going to look at how speed and velocity are treated in AP Physics. Speed is defined as distance over time. And as long as you're dealing with speed, which isn't a vector, you can do all you want with this equation. We like to write it this way, actually. V equals d over t. Now, the V actually stands for velocity, but in this case, we don't like to have two different variables for speed and velocity. We just use the V for both. If you're going to do any problems that involve average speed and you're not worried about vectors, that is direction, then this is what you do. Let's do an example really quick. How far can a cyclist travel in 2.5 hours along a straight road if her average speed is 18 kilometers per hour? Okay, so basic problem-solving technique says that the first thing you do is you got to identify the givens. So if you look here, we've got a number here, and we've got a number here. The first thing I want to do is identify what are these numbers. 2.5 hours is a time. 18 kilometers per hour is a speed. This is why knowing units is so important, because it helps you identify what kind of quantities you have. Now, the other thing that I have to identify, what they're asking for, and it says how far. So what they're looking for is the distance. Okay, now that I have two knowns and one unknown, and I've got this relationship over here, I'm going to write this down because this is what is going to relate these three variables. So now all I have to do is solve it for the variable I want to know, which is distance. Now, the easiest way to do that would be to multiply both sides by t. If I do that, then my distance is going to be the velocity times the time. Now I can substitute. So I'm going to take d equals my velocity, which really it's actually just the speed in this case. 18 kilometers per hour times 2.5 hours, and that comes out to 45 kilometers. And that's an example using average speed, no direction involved. All right, now let's look at the difference when it comes to velocity. Velocity is a vector. Velocity has direction. So we introduce something that you're not going to see in the other class, which is, instead of talking about distance, we talk about something called displacement. So we have the same idea, but we're using this word displacement instead. What is displacement? Displacement is a length. It's measured in meters. It is a distance. However, it is a vector. It is a change in position of an object. So you can go from right to left, or left to right, or up and down. And that makes a difference when we're talking about displacement. To get fancy, we call displacement delta x. The delta means the change in, and x for us in this situation is position. In our class, we're going to use for positions, we're going to use x positions, y positions, and z positions for the three coordinate axes. But for now, we're doing one-dimensional problems, so we're just going to stick with delta x. Anytime you see that delta, what that means is that we're going to take the final of that quantity and subtract the initial of that quantity. Now, in our class, I'm going to use a little zero for initial. The zero stands for where I'm at when the time equals 0. You will see other texts and places where they'll use an I instead. I don't like the I. It doesn't matter. It means the same thing, but I just kind of was taught with the 0, and that's what I like. And I believe that's also what's in your textbook and also in the AP equation sheet. So we're going to stick with that. Even if I'm wrong, that's what I like. All right, so this equation becomes the change in position, I'm going to write it this way, over time. This is more precisely the definition of velocity. And we're going to do an example so you can see how that works out differently. Okay, let's read this. The position of a runner as a function of time is plotted as moving along the x-axis of a coordinate system. During a 3-second time interval, the runner's position changes from x1 equals 50 meters to x2 equals 30.5 meters. what was the runner's average velocity. Okay, same as before. The first thing we have to do is identify what we have given in this problem. And I've got this number, and this number. So let's identify those. Two of them are identified already for us. The first one isn't though, and it's our time. 3.00 seconds. Then we've got position x1 and x2. Now I'm gonna change that from x1 to x0 because this is my initial position, and I'm gonna change this x2 to x final because it's my final position, so it can look a little bit more like our formula looks. Now again, what am I looking for? Well, it said what was the runner's average velocity, so we are looking for the velocity. I'm gonna write that down here to remind me that's what I'm looking for, and then now I can just pull out an equation that has all this stuff in it, the definition of velocity. And I'm going to write the delta x as x final minus x initial all over t. And since it's already solved for velocity for me, all I have to do is plug the numbers in. And I'm going to have my final position is 30.5 meters. And my initial position was 50 meters. All over my time of 3.00 seconds. Now if you put this in your calculator and do the top first and then the bottom, you're going to get negative 6.50 meters per second. So your question might be, does this negative sign really matter? And the answer is, if it was speed we were looking for, then it wouldn't. But this is velocity. Imagine in this coordinate system, here's our coordinate axis, okay, to the right is positive, right? That's our positive direction. We started over here at 50 and we moved back over here to 30.5. The direction of our motion was opposite the positive, so we actually had a negative velocity, which means in this case that we moved to the left. So it is important because it indicates direction. And as we get deeper into this year, you're going to see even more and more why these things are important. When we talk about vectors, we have to take them pretty seriously. There'll be certain occasions where we can ignore that stuff, but I'll let you know when it's safe to do so. But in the meantime, assume that all vectors direction is completely imperative.